Hello and welcome to Beamer, folks. For electronics, it's sometimes difficult to stop it from oscillating. There is always a tendency for electronics to oscillate. Fundamentally, all you really need is a signal that is 180 degrees out of phase from your signal with a little bit of gain in the circuit, and at a certain frequency you will get oscillation. The following is a collection of 5 oscillators made from discrete components, so there are no ICs here, and they are of square wave, triangular wave and sine wave geometry. They are fully worked and reliable. In fact, originally there was a collection of 6, but the 6th one proved to be unreliable, and therefore I didn't include it within this collection. And also, as stated in the title, these are inductorless, and they are of low frequency. There are 5 of them, a couple of which I've adapted, and one I had to create an original design for because I couldn't really find any helping reference to create it. And should you have any issues if you choose to make them, please let us know in the comments below and I might be able to help you through it. So without further ado, let's begin with Oscillator 1. Firstly, let's look at a Astable Multivibrator oscillator. The circuit diagram on the top left-hand side is the conventional configuration for a multivibrator oscillator. It represents just 2 transistors, a few resistors and a couple of capacitors that determine the timing, and it produces a square wave. Well, this is very commonly understood. There are many circuit diagrams and information on this type of multivibrator. I wanted a greater challenge than that, so I elected to use SCRs, and as you can see, the alternate flashing T10 LED car bulbs are driven using SCRs, and they are silicon controlled rectifiers. An SCR is fundamentally a diode that goes into forward conduction when the gate or trigger is applied. In AC conditions, which is where SCRs are mainly used, there is of course a reversing of supply, and that turns off an SCR. In a DC environment where there is a constant voltage, an SCR will stay conducting because there is no trigger or node to turn it off. But there are 3 ways to turn off an SCR, and incidentally SCRs have been used in power engineering, electronic engineering for decades, and they are a very mature, reliable device. But in recent years they've been eroded by FETs. Once an SCR is conducting, you can switch the device off by one of 3 ways. One is you can remove the power. Just disconnect the anode or the cathode of the diode and the SCR will switch off. The other way, second way, is that you can reverse bias the diode, and this is, as I just said, used a lot in AC because it's alternating. Half the cycle is in reverse and that will switch the SCR once conducting off. And the third way, which is slightly more unknown, you can reverse, you can spike, negative spike the trigger so that that will turn off the device. So there are 3 ways there. So let's now go and have a look at my design, my schematic of this multivibrator and its associated scope pictures. This is more or less self-explanatory. The top left-hand side represents a circuit diagram of my SCR Astable Multivibrator circuit, and on the lower right-hand side this represents the scope traces. The yellow trace is the anode of both of these SCRs, and the blue trace here represents the cathode of these Zener diodes. Let's just go through the components on this circuit diagram, starting from the left hand side. You've got here a 12 volt DC supply, a decoupling capacitor of 100 microfarad. There are two of these car T10 LED lamps. You've got here you've got an SCR, which is the TIC 106D, two of those. On its gate is a 2.7K resistor. This holds down the gate, making it less sensitive, because these devices are quite sensitive, so it keeps the impedance down low, and that's true of that resistor there as well. It just holds the gate down. The next component is this resistor here. That is, and in fact it's the same for this one here as well, the 10K, and that is important because whilst I said there are three methods of turning off an SCR, there's actually a fourth in connection with one of the three, and that is that if an SCR is turned on, if you go below a holding current, which in this case is I think about 10 milliamps, an SCR will turn off. It's not that dissimilar to unplugging an SCR from the circuit. That will most definitely turn it off, which is one of the three. So it's a kind of extension to one of those three options. But those two 10K resistors are in there just to make sure that when this is asked to be conducting, the device at a minimum will conduct via this resistor here. Because bear in mind that an LED is not a fixed resistor. In fact, below the current which lights an LED, the resistance is actually quite high. It's only when the LED starts conducting does the impedance drop. So that's why that little important resistor is there. The next resistor here is to do with the timing components. The two timing capacitors are this one here and this one here. They're 22 microfarads. And so you've got a CR network going on, a timing network between C3 and R2, and then you've got C4 and R4, the 18K and 22 microfarad. We come to this capacitor here. This is the all-important part of this circuit, because other than that, this looks very similar to a conventional transistorized multivibrator circuit, except for this capacitor here. And this capacitor here is called a commuting capacitor. And what it effectively does is commute what's going on from one side here through to the other. And this enables one side to switch off the other side. And when the other side switches off, that is communicated through to the other side here. The Zener diode here, in association with this resistor here, and it's true of this side as well, is a 7.5 volt Zener diode. And what that does is it offers a high impedance for the charging circuit initially until the Zener voltage is exceeded. Plus, I think it's about 0.75 of a volt here for the gate. So you're looking at about 8 volts. At 8 volts, when the timing circuit voltage exceeds 8 volts, it will turn on the SCR, and that's true of that side as well. Let's just now go through the dynamics of this circuit. As it's a loop, it's always a bit tricky, but let's give it a go. Let's assume that this has just turned on, that's conducting, that SCR is conducting, and this SCR is turned off. So this LED lamp is lit, and this LED lamp is now not lit. As this has just gone down to 0, this side of the timing capacitor has also gone down to 0, bringing this side actually slightly below 0, so it's slightly negative. The capacitor starts charging through R2, which is an 18K, and when it reaches about 8 volts, that will trigger this SCR. When that triggers, that will pull down this LED lamp, lighting this lamp up. And because this has gone from a high to a low, that is passed to this commuting capacitor, making the other side of that capacitor suddenly drop to 0. And in fact, the other side goes actually negative by quite a way. It's a spike that occurs. It's a differentiated signal. And that negative spike spikes negative the anode of this first SCR, effectively turning it off. As this is now turned off and gone high, and of course this SCR has turned on, this side of the capacitor has now suddenly gone to 0 volts. That 0 volts is taken this side of the capacitor down to 0, and it will start to charge. This capacitor will start to charge up through R4, which is an 18K, and that will start to charge until it reaches 8 volts. This SCR now conducts, pulling that side of this side of the LED lamp down to 0, lighting this lamp, and that information is commuted through this capacitor as a negative spike, turning this SCR off. There is additionally to the anode negative spike turning off issue, because the charging circuit operates in a fashion that also makes, at the point of wishing to turn this SCR off, it also goes at this point here very slightly negative by I think about 5 volts. That forward conducts the Zener diode and pulls the gate down through to negative as well. So in this circuit, each SCR has 2 of the conditions that I said of the 3 conditions that would turn an SCR off. So you've got the security of making the gate negative to turn off the SCR and a negative spike on its anode to also turn off that SCR. So it has 2 means of switching this off, giving this very good security in turning this off. So they never both turn on at the same time. On power up, which is always an issue with multivibrators, if all these components were absolutely identical in every way, the SCRs, the capacitors, the LEDs, the resistors, etc., on turn on with a multivibrator, it's got an Achilles heel, and that is that if they were all identical, you could get a race condition that never puts one of these on and the other one off. They could either be both on or both off. It's because there is asymmetry going on here that component values are different. A race condition runs on switch on, and that one will always turn on just fractionally before the other, initiating the cyclic nature of a multivibrator. All multivibrators, as far as I know, suffer from this Achilles heel, and it's very rare that when you turn a multivibrator on that both can actually turn on, but it is a possibility. And if you were designing this into a critical circuit, you must build a method in which, if that happens, that one of these will be triggered. Let's now look at the scope traces. These are of one SCR, and let's say for argument that it's this SCR here. You can see to begin with that there is charging occurring on the cathode of its associated Zener diode. And if this is 0 volts, which it is, you can see it starts off in a slightly negative position. I think it's about minus 4 or 5 volts, because it's 5 volts per division. And you can see that it's ramping up in an exponential manner through R4. When it reaches the threshold voltage of about 8 volts, you can see that it triggers, it turns on that SCR. And you can, if you look at the anode here, you can see superimposed on the anode, the reflective charging that's going on here. And when it reaches this point here, the Zener diode turns on. You can see it's a very clean turning on. It runs for a duration that on the other SCR is going through its timing up period. When the other SCR reaches its threshold gate voltage and turns on, I don't know whether you can see this, I can just about see this, but there is here a very sharp, very faint spike, and it represents about 3 divisions, so that's about 50. I would guess it's about 12 volts, and that turns off this SCR, and as you can see, then the cycle repeats itself. A phase shift oscillator, well, that name accurately reflects how this oscillator works. I'll first describe what we're looking at here. First of all, we have the basic circuit diagram on the left hand side, and on the right hand side we have scope traces. The yellow trace is taken from this point here, and the blue traces, and there are 3 of them, and that is the reason why there are 3 dots here, T dot being that one, M dot being that one, and B dot being that one. Top, middle, bottom. I'll explain this circuit from the left hand side. First we have the decoupling capacitor here, which is common to all my circuits. Next we have the all important phase shift network, and that feeds into a JFET offering a high impedance. Next we have this transistor here which gives us voltage gain, and finally we have Q3 here which buffers to the outside world. It ensures that whatever happens on the output here doesn't interfere with the fundamental frequency of this oscillator. Okay, so let's now get more into the nitty-gritty of this circuit. Let's first of all look at the all-important phase shift network. These capacitors here, 4.7 nanofarad, are identical. They must be identical. And the resistors, which are 12K, there are 3 of them, and they are identical. And if we move over to the scope traces here, with reference to the output, which is the yellow here, you can see that when we go through the first RC network, that there is a phase shift, and each phase shift, each element here, phase shifts by 60 degrees. And you can see that the first element shows a 60-degree phase shift, and then we get to a 120-degree phase shift, and then finally down here we have a 180-degree phase shift. If we jump forward one section and go to the voltage gain, you can see that between the base and the collector there is always a 180-degree phase shift. So as this feedback is feeding the beginning of this network, it is 180 degrees. Well, if you add 180 degrees across the transistor and 180 degrees across the phase shift network, you end up with a number of 360 degrees or 0. So this circuit is in a sense self-feeding. If you apply gain to that type of circuit, at some point you reach a gain where the circuit will start to oscillate. That gain is set here. You've got a DC gain which is set between this resistor and this resistor here, but an AC gain which is set by this resistor here and this capacitor here. And the overall gain of this is approximately 25. If the circuit doesn't oscillate, you've got insufficient gain. You would need to decrease the value of this resistor. If the output signal becomes distorted, which it will do if there's too much gain, you would have to increase this resistor to reduce the gain. Some people put a potentiometer in there and that's perfectly fine, but I find the adjustments to be quite coarse, and I prefer to put a fit on test resistor on the side of this capacitor here to gently shift the gain till it oscillates and produces the best waveform that can be achieved. Now, the phase shift network really requires two facilities. One is that it needs to be driven from a low impedance, relatively low impedance, and the output of this phase shift network really needs to see as higher impedance as possible so that the sensing circuit here doesn't load the network down. You can actually build a phase shift circuit with just a single transistor, and I've seen that applied to a tremolo feature of a valve amplifier. But I've added two extra components. I've modified that. One is to include the JFET so that it offers a very high impedance, and the second thing I added was a buffer here. The feedback here is probably the weakest point of this circuit, in that it doesn't offer a very low impedance drive. To achieve that, you would really need to use an op-amp, but because we're looking at discrete components here, I had to strike a compromise. The frequency of oscillation can be altered relatively easily by adjusting these components of the phase shift network, bearing in mind that they have to be the same, as I mentioned earlier. You can increase these capacitors, you can reduce these capacitors, you can increase these resistors, you can reduce these resistors. The network itself can become quite a low impedance, so the relatively higher impedance here of maybe 1,000 ohm or slightly more, a couple of thousand ohms, imposes a limitation as to how low of an impedance this network can be set. So you're better off with higher value resistors, smaller value capacitors. Originally, I could have taken the input to the phase shift network from here, from this point here at the collector of Q2. I could have, and in fact I did, take it through to the emitter of Q3, and that offered a significantly lower impedance. But I moved away from that idea simply because I don't like the idea of unknown things going on here affecting the fundamental frequency of this oscillator. Now, moving over to the scope traces finally, one thing that stands out like a sore thumb is the wave shape on the output of each phase shift element. And on the first one, it's kind of sine wave, a bit distorted, but you can see the deterioration of the sine wave to finally feed into the JFET. And the quality of the sine wave, even though this is the best that I could achieve, seems to me quite consistent with other phase shift oscillators to be very slightly distorted, leaning to the left. Perhaps it is a function of tolerances going on within the RC network, within the phase shift network here. I thought I'd show you a fast Fourier transform of this sine wave. And as we said, the sine wave looks very slightly distorted. The center frequency here of 5 kilohertz I've put in there simply to move it away from the center crosshairs to over here. Hertz per division is still 1 kilohertz. So we're looking at a center frequency of this oscillator producing 1.09 kilohertz. But if you look at this closely, this is incidentally a flat top window representation. If you look at this closely, you expect for a sine wave there to be even harmonics all the way up and down. Well, the down I can't quite show you. There are limitations with these scope FFTs. But if you look at this down here, this in theory is the second harmonic. But you can see there's these little peaks here which are rather strange and not normally present in a sine wave FFT. This is the third oscillator. It's a programmable unijunction transistor called a PUT oscillator. It's a bit of a blast from the past because the device, which is a 2N6027, is virtually obsolete. But I've included it because I've worked with this in the past and it's quite an interesting relaxation oscillator. It has been largely usurped by the infamous 555 chip. We can see before us on the breadboard that there is a blue LED, well, that is just indicating that the supply is on, and a green flashing LED, well, that's flashing at about 1 second. You can also see that this transistor is driving not only the green LED but also two very small speakers, and if I'm quiet you'll be able to hear, hopefully, a clicking in the background. Hopefully you've heard that clicking, it's a little faint. You can also see that there is a 100k potentiometer that I'm twiddling to adjust the frequency of the flashing. It can vary from about half a hertz through to about 1.5 hertz. With this device you can adjust quite considerably, and I'll go into that in a minute when we look at the circuit diagram and associated scope traces. Okay, before us we have the circuit diagram on the left hand side here for the programmable unijunction transistor relaxation oscillator, or thank goodness for short, PUT oscillator. And on the right hand side we have the circuit traces. This is the basic waveform, yellow being this spot here, blue being this spot here, and this is a zoomed in version of this. This is running at 200 milliseconds and that one's running at 100 milliseconds. The frequency is nigh on spot on 1 hertz, and that was adjusted by VR1. Okay, so let's go through this circuit. On the left hand side we have the timing capacitor, 10 microfarad. Then we have the timing resistors, which are in series, the 47k here and 100k potentiometer. Down here is the PUT, which is the 2N6027, and on the cathode of that drives the LED, the green LED, and that's in series with, this is drawn as one speaker, but I used 2 speakers because I thought both of them were 8 ohms, so I thought a 16 ohm load would be more kinder to the circuit. The 2 resistors here are interesting because they set intrinsic standoff ratio of this programmable unijunction device. The device is very akin to a silicon controlled rectifier. That is, that it behaves when conducting as a forward conducting diode. The voltage here, which I should have put on here, is at this point here 6.1 volts DC, and that sets the point at which the capacitor charges up to before it is triggered, and that is defined by those 2 resistors, and you can see that this one is approximately half the value of that one. And of course on the right hand side is my decoupling capacitor of 100 microfarads. The complexity of the timing, I'll just indicate how complicated this is, and I researched a formula and I couldn't find one that actually worked for me, so I did take the information I could find and adapt it slightly to what I thought to be correct, and it seems to work quite well for this. And because I've constructed it, you need to apply a slight reservation there. The word programmable used by this device, in our modern world we tend to think of it digitally, but this really is a misnomer here. In fact, I would probably call it voltage controlled unijunction transistor. Moving over to the scope traces here, you can see at this point here, the blue point, that the capacitor is exponentially rising and then being reset there, typical relaxation oscillator. The yellow trace, which is the cathode of the PUT, is a very powerful little short-lived spike, the amplitude of which is about just over 6 volts. Well, that makes sense because this capacitor is being charged up to that level, and it discharges that capacitor quite powerfully into the speakers and the green LED. I could calculate the power of this, but it is limited by, of course, the impedances of the various components in the line, including the resistance within the capacitor itself. But you're quite welcome to do, what is it, half CV squared or Q equals CV, Q equals IT, and can calculate this. But the number is actually quite large in terms of current. But bear in mind that it is limited by the intrinsic, appropriate word for this device, and intrinsic resistance values in this path. I thought I would just add that this is the way I think of this rather interesting little near obsolete device, is that when it triggers, just kind of mentally think that all these 3 terminals join together in a short circuit, and that discharges that capacitor into the load. Oscillator number 4, a Wien Bridge oscillator. This hardly needs an introduction. It is just so popular, and there's an awful lot of information about this on the web. But I've adapted the circuit slightly. I feel as though I've improved it, and that is the reason why I've included it. Its popularity is for a reason, and that is it can, when trimmed, produce an extraordinarily good sine wave image. Very low distortion it can be. Now we go on to the circuit diagram explanation. First of all, I go over the components, and then I move into an explanation of their significance. Firstly, on the left hand side we have my ubiquitous decoupling capacitor here. Then we have the Wien Bridge that represents these 4 components here, R and C, the C being those 2, the R being these 2 here. And then we move on to a JFET configured in a drain source configuration, followed by an inverter and voltage gain stage. Then we have a gain adjustment here using a 10K potentiometer in parallel with a 33K, followed by my buffer, which is here, and the output of the buffer goes to the outside world. This circuit is not a million miles away from the phase shift circuit I did earlier. Let's look at this circuit in finer detail, particularly the Wien Bridge, these 4 components here. Well, the first series components here, these 2, this resistor, this capacitor, is in series with the feedback loop from the transistors. And these 2 components, the R and C, are in parallel, and they represent another circuit. Both the resistors need to be identical, and both the capacitors need to be identical. This combination here, C3 and R1, represent a high pass phase lagging circuit, whereas these 2 here represent a low pass phase leading circuit. And as you've probably worked out, there is a point of equilibrium here, point of balance, which describes the frequency at which the Wien Bridge oscillator oscillates. And at that point of balance or equilibrium, there is 0 phase shift between the feedback here and the gate of the JFET. In principle, you just really have 2 filter networks, one series and one parallel. Moving on to the JFET, we are in a drain following configuration, and this represents fairly little gain in itself. The voltage gain is all in this transistor circuit here. And by the way, because you're coming out at the drain, there is a 180-degree phase shift between the gate and the drain. And as well as a voltage gain circuit here, this is also 180 degrees out of phase between the base and the collector of this PNP transistor. The collector load of that transistor, rather uniquely, and this is my design, the gain of which, this transistor, is adjusted in its collector, not its emitter. And for this circuit, that represented an advantage. Also, this is a point where the feedback goes into the series network here and is connected through to the base of the buffer, which prevents anything going on here with its output interfering with the frequency resonance of the Wien Bridge oscillator. Regarding the Wien Bridge itself, there's a peculiarity with Wien Bridge networks, and that is that whatever signal's coming in here, by the time it's arrived at its equilibrium point, zero phase shift, at this point here is almost exactly a third in terms of voltage peak to peak as there is on its input. And that is true no matter how you change these components here, the R's and the C's. They always have to be identical, the R's and the C's. It is of a zero phase, and that is important because, as we just said, we've got 180 degrees across here and we've got an additional 180 degrees across here. Well, the sum of those two is 360 degrees or 0 degrees. Now, if there is a third drop between the input of this Wien Bridge and its output, to make this circuit oscillate, we have the primary ingredients of a 360 degree phase shift. But we've got a drop in voltage here between those 2 points. To make up for that drop, you need to have this little amplifier not only 360 degrees, 0 degrees, equivalent to, it has to have a gain of a minimum of 3 to make up for that loss. And in fact, usually Wien Bridge oscillators would like something in the order of 3.1 gain. So you need just a little bit above the loss made up in this network to make the circuit oscillate. So I'm describing something that is actually quite critical, and that is true. I've mentioned it up here. So we need and I used a 10-turn potentiometer here. If you have the gain too low, the oscillator will be damped and it never reaches continuous oscillation. If you have the gain too high, you reach a point where the oscillation is distorted. Well, obviously somewhere in between the two is the point that you're after. And you can trim this very finely to produce an extraordinarily good sine wave, much better than the phase shift oscillator. But now we'll move on to the circuit traces. Before we go on to the circuit traces, I'd just like to add a couple of things. One is, when I was referring to gain, I was referring to AC gain. The DC gain is continuous and stable. The AC gain is the one you vary with VR1. The other point I would like to make is that the Wien Bridge oscillator really requires two features of the circuit, and that is that there is a low impedance driving it and a high impedance seeing it. Well, I've accomplished the high impedance. This is similar to the phase shift oscillator. I've achieved that via using a JFET. It's a very high impedance here and doesn't load down the filtering networks here of the Wien Bridge. The driving impedance here is quite low, but not very low. It would probably be better served again with an op-amp, because that would have a lower output impedance. But providing you keep the resistors relatively high value and capacitors relatively small, the circuit should be fine. Right, let's move on to the circuit traces. At the top here, the first trace, you can see the output quality from here, the yellow spot, and you've got additional comprehensive information at the top here. You can see that the quality of this sine wave is superb. It doesn't lean to the left, it doesn't lean to the right, it's not over peaky, negative or positive, and there is no clipping going on here. It probably is not the best that can be achieved, but it certainly is the best that I could achieve. Going down to the second trace, which I personally find more interesting because it highlights the difference between the input of the Wien Bridge and the output. You can see clearly here two things. One is that the input to the JFET is about 500 millivolts per division. So you're looking at about 1.3, 1.4 volts against 3.92. Well, that is approximately a third. And bearing in mind that this is continuous oscillation, so it would have to be very slightly higher than the absolute minimum. Secondly, you can see that the phase between the output here and the input is 360 degrees, or in fact 0. The peak here on the blue lines up with the peak on the yellow. Going down to the third trace here, this is an FFT window flat top of the output. And you can see that the output is again displaying a superb sine wave. And if we look at the FFT itself, you can see that the peak at 1 kilohertz is here, and there is a gentle decline going to the higher harmonics. I have to say, looking at this, that it's not reflecting the peaks on even harmonics rising in frequency. I don't know whether it's because I chose a flat top window, but it's not shown. They should be. A sine wave should display even harmonics all the way up, not odd harmonics. And what I'll do, if I can make an improvement upon this by changing the window, I'll put a link to that in the description below. Finally, oscillator number 5, a Schmitt relaxation oscillator that superficially thinks it's a 555. I'll begin by going through the circuit diagram, initially broadly so, and then I get into finer details. Firstly, we have the timing circuit, and that's formed by R2, R3 and C1. We then have the Schmitt Trigger that is formed by Q1 and Q2. These are NPN transistors. The final transistor, which is a PNP transistor, is Q3, and that forms the output drive. Well, that's the basics out the way. Let's get into the nitty-gritty. R1 is a pull-down resistor for the output transistor Q3 on its collector. R3 is C1's charging resistor, and it's via a diode. And R2 is the discharging resistor. So when the output's at a high, that resistor is engaged with a load of R2 across C1. But when the transistor turns off and is pulled down by R1, D1 is reverse biased, and we're left with just C1 being discharged by R2. Whilst there is a tremendous amount of information on the web regarding a Schmitt trigger, I'll just go through the basics so that we can see what's going on here. In principle, these two transistors are kind of digital in the sense that when one is conducting, the other one is always non-conducting, and vice versa. And on the input here, on the base of Q1, you can have an analog that varies quite considerably. But if it reaches a certain threshold, these two transistors switch over. And when they switch over, they operate the trigger conditions in such a way as to encourage the switching. But the analog input has to be exceeding that of the trigger level. If the analog level is lower than the trigger levels, then these two transistors will never change states. The function of the input that I've just described about encouraging a trigger level is called hysteresis. And hysteresis is what a Schmitt trigger is all about. Let's now look at the scope picks. The yellow trace here, yellow trace there, is at this point here the yellow spot. So when we look at this, this is the square wave generated by our Schmitt oscillator. It goes between 0 and nigh on plus 9 volts. The rise and fall time actually look very sharp on here, and indeed they are. One of them is of a low impedance source, which is Q3, turning on. The falling edge here, negative going edge, is limited by the fact that it is a pull down resistor, which is R1, and that can impose limitations. If you have a capacitance on here, the rise time would still look nice and sharp, but the fall time would have a slope on it, and as the capacitance increase, so that slope would increase. Moving down to this trace here, which is a blue T, so we're looking at the blue T spot, which is that point there, and that is of course measuring the voltage across the timing capacitor. So this is the timing curve that's in sync with, of course, naturally, the output. And the base of this voltage here, signal here, is at 3.56 volts, and at its peak it is 5.9 volts. So we're looking at a difference of about 2.4 volts. You've got an exponential rise all the while Q3 is switched on, and then we got an exponential fall all the while Q3 is off. Well, that of course is describing when Q3 is switching on, it's charging the capacitor C1 through R3, and when the Q3 turns off, it's disconnecting that resistor because this is going down to 0, so that is reverse bias D1, and C1 is being discharged through R2. When we go down here, we're looking of course at the yellow spot output there, and when we come to here, this blue trace, which is blue trace M, of course is blue spot M here, which is the voltage that's being developed across R5. At its high point, which is when Q3 is conducting, you've got a voltage here of 5.1 volts. When Q3 is not conducting, you've got a voltage across R5 of 2.8 volts, and that represents, with Ohm's law, a current difference between, at this state here, 1.5 milliamps, and at this point here, 0.85 milliamps. And that is very important because it shifts the trigger level on the base of Q1 in a hysteresis way. If we look at the two legs of Q1 and Q2, that is the series resistor loads on the collectors of each, you'll notice as this is a series of 2.7 plus 1K, which is 3.7K, as opposed to this collector load of Q1, which is 6.8, there is approximately half the resistance load on Q2 as there is on Q1. And that is why there is a difference between 1.5 milliamps, which is this path here, and 0.85 milliamps going through there. And that is reflected across R5. And that is essential for a Schmitt trigger, because the hysteresis that we spoke about going on the base of Q1, the threshold is being shifted by the two states of current arms that are feeding into R5. So all the while you've got 1.5 milliamps flowing through here, the threshold is high. But when it switches over to here, the current flowing through R5 is 0.85 of a milliamp, and that ensures that the threshold, the trigger point, is dropped nearer to 0. Let's now go and have a look at the FFT. It is window flat top, and the frequency per division is 2 kilohertz. And we can clearly see here, this is set to more or less 1 kilohertz, that typical of a square wave, you have dominant third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, and then the evens start picking up. And I don't know how true this is, but that is pretty reflective of a square wave. A square wave can produce every frequency under the sun, and it's only limited by the rise and fall time of those edges. Quite remarkable, and this shows it actually quite well. I'm quite pleased with that. I hope you've enjoyed my bucket full of oscillators, and if you felt so inclined, can you please like, share and subscribe to my channel. Thank you. This is Beamer signing out for now.